All right, thanks for coming. My name is Ming. So today I'm going to talk about the one of the problems with distance-based method. If you are using, I guess most of the data mining algorithms are using distance measure. All right. So I'm going to convince you that the distance measure have alternative measure now. Okay, so the alternative measure is called the mass-based measure, or it's data dependent. Okay. Now, this is the content of the talk. I'll give a brief introduction about the existing weaknesses of the algorithm using distance-based methods. And the cause of the, I'm going to assert that the cause of the problem is the use of distance measure. All right? And then I'm going to introduce that there is an effective alternative to distance measure. Right? That is the data-dependent dissimilarity. And then I'm going to provide you with evidence using 3 existing distance-based algorithms. And all I do is that I unplug the distance function and plug in the data-dependent dissimilarity. And all the rest of the algorithm is exactly the same. And then you can actually see that it will overcome the weaknesses I'm going to show you later. Okay? So what that means that is, in fact, there is a change of perspective fundamentally of what you mean by nearest neighbor or most similar neighbor. Okay, so this is the content of my talk. So what you see in front of you are 3 algorithms in 3 different tasks. The first one is the clustering algorithm based on density. Okay, we all know that. In fact, this is a known problem for years. If you're using density-based clustering algorithm, the density-based algorithm has the difficulty to identify all clusters if your data set has greatly varying densities. All right? So there's a lot of algorithm try to overcome this if you are using density-based algorithm. Now, and the second one is the k-nearest neighbor anomaly detector. Again, this is a known problem. And there's a known solution also. All right? They try to detect if you are using nearest neighbor, you can actually, there's a problem, you can detect local anomalies. And then there is the k-nearest neighbor classifier. All right, again, this is, well, this is less well known, but this is a known problem to us due to the likelihood estimation of the k-nearest neighbor. So what is common to these algorithms here? Well, they all use distance function. Okay? And so we all know that if you use distance function, you compute the dissimilarity of 2 points solely based on the geometric position of the 2 points. All right? And the data distribution, doesn't matter. All right? You could have very skewed, very uniform, or multimodal. It really doesn't matter. Okay, that is, what that means is that the distance function is a data-independent measure. Right? So I'm going to assert that the distance measure is the root cause of the 3 weaknesses I told you earlier. All right, so look at this example here. So this is a data-independent distance measure here. So what you see at the bottom is the typical epsilon neighborhood function people use to estimate density of a point. All right? So if you're using this particular function, well, a very important thing is that you have to fix the epsilon value. Right? Once you fix the epsilon value, of course, the heart of that is the distance function you use. So I see here is the LP norm. When you set p equal to 2, that will be the familiar Euclidean distance. All right? So as I said earlier, if you use this function, you have to have a fixed epsilon value that determines the radius to identify. Within this radius, you're going to count how many points in there to estimate your density. All right? And in estimating density, as you know, you need to know the number of points divided by the volume in order to get the density. In order to avoid the volume calculation, you want to make sure that all the volume you have is constant so that you can avoid estimating the volume. So make your task of estimating densities a lot easier. That's why the epsilon have to be constant. All right? So what I propose is that you can actually use data-dependent dissimilarity rather than the data-independent distance measure. So what you do here is that I'm going to use exactly the same function, except I pluck out the distance function and plug in the mass-based function. I'm going to give you the definition of mass-based function in a minute. But I'll give you some of the concept here. So similarly, right, there's a mu, which is some kind of radius, if you like, for the function. So exactly the same example here. You can look at it. The boundary here, in fact, are quite different from what you get if you're using distance function. All right. So what is sort of very obvious here is that in the dense region, you got the volume, in fact, significantly smaller than in the region of or in the sparse region. Right? For example, this region here is sparser than the one before. You get a bigger volume. And then in the very sparsest one, you get even bigger volume. All right? And you look at the boundary point. What that means is that the boundary point has the same similarity to the center x. Right? Also, what that means is that if you have two equal distance points, for example, z here, z is now more similar to x than y is to x, although both of them has the same equal distance to x. Yeah? Okay, that is the key difference between using distance measure from the data-dependent dissimilarity measure. So what is the data-dependent dissimilarity measure? So the key here is that it computes the dissimilarity between 2 points based primarily on the data distribution around and between them. Okay? So once you do that, what you do is that you fundamentally change the way you identify similar neighbors. And if you do that, then if you simply, as I say, if you simply replace your existing algorithm, unplug the distance function and plug in the data-dependent dissimilarity, it will actually overcome the key weaknesses you have now, particularly in data set that you have greatly varying densities. So I'm going to briefly introduce the generic definition of the data-dependent dissimilarity. It is, in fact, an extension of mass estimation I introduced in this conference in 2010. So what it does is that it actually extends from the mass estimation of 1 point to this similarity of 2 points. Okay? And we have, in fact, introduced a first version of mass-based dissimilarity in ICDM in 2014. Okay? And what we give it here is a generic version of that. And the one in 2014 is a special case. So as you can see here, there's a fundamental change here. In terms of measuring distance between x and y, okay, what is important here is For example, this is an example. I hope at the back you can see the 2 points at the bottom. So if we want to measure distance here, we are not going to measure distance, with any path from x to y, right? Okay, that is the fundamental thing in here. What we want, in fact, is the shortest distance between x to y. Okay? If you're going to use a data-dependent dissimilarity, then the fundamental or the primitive you're going to use, in fact, now is the smallest local region covering x and y, not any local region bigger than that. Okay, so there's an analogous here. Rather than using the shortest distance between x and y, now the primitive becomes the smallest local region covering x and y. So that's the primitive of the function. So come to the definition. So let's say you've got D, which is a data sample. You sample from the PDF F. And then you get some kind of model H, where it is a hierarchical partitioning model of space into non-overlapping and non-empty regions. All right? So you got two things in there. Now, what is the smallest local region? The smallest local region is defined as in equation 1, where you try to find the smallest region in H that covers x and y. That is the definition. All right? And then once you got the smallest local region covering x and y, then all you have to do is find out the probability mass of that region. Okay? And then, because you're going to use different models, you're going to do the expectation. What you really want is the expectation probability mass of that local region of multiple models. So the expectation is taken over all possible models. Now, make it simpler. Of course, in the real world, we're not going to eliminate all the possible models. We're going to use a fixed amount of models to do the estimation. So let's say you got a H1, and then from H1, you were given x and y, and then you find out the smallest local region covering x and y. Okay? And then once you got that, you estimate the probability mass of that local region. Okay? And then, you're going to have T models, you average over them. That will be the probability mass of x and y. That's the way we're going to do this. And in this particular case, I should say that the genetic definition you can implement in different ways, okay, including the one we reported in 2014. But in this particular paper, we're going to use iForest, okay, the one we introduced in 2008. So as the name suggests, it is a tree structure. So in a tree structure, it's going to divide the space into non-overlapping and non-empty regions. Once you got that, then all you have to do, because it's a tree structure, you got x and y, then you pass through the x and y to the tree up to the lowest node in which x and y contain. Okay, and then you compute the probability mass on that node. Okay, so then you just average them over T trees. That is the implementation we're going to use. Now, this is one example, graphical example of what is an I tree here. So let's say you already built a tree, and there are 4 examples in here. Now you want to find out the similarity of B and C. All right. So in this case here, the B and C, at that node here is the smallest or the lowest node that cover B and C. So in this case here, the mass will be 2. Now let's say you want to find out what is the probability mass or the similarity between, or dissimilarity between A and D. Then then at that node, in this particular show here, is the lowest it's the smallest local region that cover A and D. All right, so in this case here is 4. And what is interesting from the distance measure or any measure which is a metric is that the cell's dissimilarity is not a constant. So it's different from not only the distance measure, but also from any other metric measure we now know. Okay, so in this case here, as you can see here, the cell similarity for A to A is 1, but cell similarity of B to B is 2. All right, in other words, the cell dissimilarity is data dependent also. All right, by the way, to link it back to the original source of mass estimation, the cell dissimilarity, in fact, is the mass distribution. So we apply that to 3 tasks. So the first one I'm going to show you is the density-based clustering. So for example, dbScan. All right? So we all know that dbScan is unable to find all clusters of varying densities. And in fact, from what I know, nobody knows exactly under what condition dbScan will fail to do that. In fact, we have a paper on that actually tells you exactly under what condition dbScan will fail to find all cluster in the varying density condition. So this is the example in which dbScan will fail to find all 3 clusters. So in this case here, we got 2 dense clusters and 1 sparse cluster. As you know, the dbScan will use a global threshold to find the density. Okay, so in this case here, you got only 1 cluster, but the other 2 will be the 1 dense clusters. Now, all you need to do here is change the distance measure to the mass net measure. Okay, so now you use exactly the same data. What you get on the right-hand side is the mass distribution. As you can see here, the mass distribution has 3 clusters in which you can actually use global measures to identify all clusters easily. Okay? So because of time limitation, I'm going to skip the next 2 applications and straight to the, I want to talk about this actually, the fundamental change in perspective. So we all know that we need to find, given a point, we want to find the closest matched neighborhood. All right? And because we are familiar with distance, we're going to always, almost always we use the distance function. What that means is now, for x, we want to find the nearest neighbor. Okay? But if you now change to use the data-dependent dissimilarity, then your most similar neighbor now is in fact defined by the lowest probability mass. Okay? So what you get here, if you got the k nearest neighbor, if you just change the distance measure to the data-dependent measure, what you actually get now really is a k lowest probability mass neighbor algorithm. If your algorithm is density-based, such as the dbScan, by simply doing that simple change, although exactly the same algorithm is used, what you actually change from a density to mass-based method. Okay? There's nothing changed in the procedure, but only the dissimilarity measure. So the implication. Right? The implication is that the dissimilarity measure are assumed to be a metric as a necessary condition for all data tasks. But this work shows that the assumption can be an impediment to produce good performance model in 3 tasks. So conclusion, the proposed data-dependent dissimilarity measure overcomes the key weaknesses of 3 existing algorithms that rely on distance. And what we show here is that you can actually transform your existing algorithm by simply replacing distance measure with data-dependent measure. And the transformation, in fact, is a fundamental change of perspective, as I showed you earlier. I should talk about it. Thank you.
Thanks. Okay, if I give it back to Pallav, anybody else? Okay.
Thank you. It's really interesting shift in perspective, really. I just wanted to have a question about the anomaly detection application. Did you do any like precision recall measurements for using this method for the anomaly detection application?
Yeah, so I'll just quickly show you the anomaly detection, right? So show you the anomaly detection example here. Okay. So, well, the precision recall or the AUC, these are measurement of the performance, basically. Yeah. So what I show here is that is the if you're using k-nearest neighbor, you were actually unable to identify local anomalies. So in this case here, the local anomalies are really this area here, right? Okay, at the bottom of the dense area. Whereas once you change it, right? So you will actually get the local anomaly will be ranked very high, almost as high as those points in here, in the sparse region. All right. So in other words, if you are interested not only the global anomalies but also the local anomalies in the dense clusters, then you will be able to find them. Right? By simply changing the distance measure to data-dependent measure.
So are you more likely to find a higher number of anomalies using the mass-based dissimilarity method?
Yeah, in this case, you will be able to find those local anomalies. So your whatever measure you use, it can be AUC, precision, you will get higher value in this case.
Yeah, quickly.
Hi. Oh, very interesting work. So I have two questions. So first question is, so you compare, so all the, I see the results, you compare your methods with the, normally Euclidean distance. But have you done any experiment, compare your method with other distance, which are capable of combining, incorporating some distributed information, for example, Mahalanobis distance. So have you done such experiment? And second question, is the code available? Yeah, is the code available so we can try it?
Okay. Yeah, good question actually. So they are data dependence measure around. For example, Mahalanobis measure is one of them. But what is the key difference between the existing so-called data dependent dissimilarity from what we propose here is that the cell's dissimilarity ours is not a constant, whereas the rest of the data dependent dissimilarity now, the cell similarity always a constant. In other words, they are metrics, whereas what we propose here is a non-metric.
Okay.
Yeah. Okay.
Take it offline.
Thank you.
Thank you. Thank you.